Today we will be discussing about a specific practical approach to implementation of uh, systems which behave intelligently. Earlier we have discussed about one form of knowledge representation, and that is logic. We have also seen how inferencing can be carried out in logic. Today we will be discussing our discussion will focus on rule based systems, which is a very practical implementation of uh, intelligent behavior. Of course, it derives from logic. We will see how it is dependent on logic and how it is also some sort of simplification to make the systems uh, implementable under engineering terms. We have seen well-formed formula in the case of propositional logic and first order logic. Now, these essentially represent assertional knowledge, or they represent assertions. What are assertions? Whenever I make a statement, today is Sunday, yesterday was very hot. These are some assertions that I am making, and these statements, as we know from our knowledge of logic, can either be true or can be false. We can say that these can be evaluated to true or can be evaluated to false. These are assertions, and we have seen that propositional well-formed formulae or predicate well-formed formulae all evaluate to either true or false. Now, if we look at these assertions in a little more detail, we can see that these can be decomposed, or these can be categorized into two different forms. One is rules, another is facts. Now, rules are assertions given in implicational form. I hope all of you remember what is meant by implication. P implies Q. Okay, that's an implication, and rules are usually given in that form. We'll soon see how the rules look like. There is another set of assertions which we call facts, which represent domain specific knowledge. Say, if the boy is intelligent, just we say the boy is intelligent. That's an assertion. It may be a true statement or it may be a false statement. But when we assume that it's a fact, then we usually assume that it's true. The boy is intelligent. But if we say that if the boy is intelligent, then the boy will score good marks. That is a rule we are saying, and this implication is being noted by this construct if then. So we can have a complete knowledge system which consists of two distinct components. One is rules, another is facts. We can have a set of facts which are presented from the domain of discourse. For example, let's consider the domain of geometry, school geometry. We can say ABC is a triangle. We can also say ABC is an isosceles triangle. AB and AC are two sides of the triangle. Now, all these three statements that I have made are nothing but assertions, but there is no implication in that. I have just said AB and AC are two sides of the triangle. I have said ABC is a triangle, or ABC is an isosceles triangle. All these are facts. Now, if I say if ABC is an isosceles triangle, then the sides are equal. If ABC is an isosceles triangle, then the two sides are equal. Now, this is a rule which I am stating, and based on this rule, using this implication that is inherent in this rule, I can infer new facts. Okay, let's go a little further. Now, in logic, we represent knowledge in declarative and static way. Okay, we just say, we make statements which are declarative, and rules in logic say what is true given some conditions. For example, when I say if ABC is an isosceles triangle, then sides AB and AC are equal. Now, therefore, using this rule, if I know that ABC is indeed an isosceles triangle, then I can infer the new fact that AB and AC are equal. All right. So, rules in logic are saying what is true given some conditions. What is the condition? The condition is that ABC is an isosceles triangle. And what am I saying using this implication? I am saying that rule is implicitly saying, therefore, AB and AC are equal. Now, rule based systems rules, these are just implicational statements in logic. Now, in case of rule based systems, we go a little one step further. Our implications, that means the right hand side of an implication, usually in logic makes another assertion. Okay? If the boy studies hard, then he will score good marks. This is an assertion. But I am not asking anything to be done. On the other hand, look at this statement. If the temperature of a plant, of a furnace, is very high, then shut the heater off. Now, look, here in the implication, I am not just making an assertion, I am also asking for some actions. Shut the heater off. So, that is also possible to be stated in a rule. So, rule based systems are based on rules that say what to do. Okay? Now, here I would like to make a distinction between two types of knowledge representation. One type is declarative knowledge representation. That means where we just say what is to be done, but we do not say how the thing has to be done. Whenever we write a program, say for example sorting a number, okay, or write a program to draw a diagram, there in that program itself we specifically mention all the steps that we need to carry out in order to perform a particular task. There we specify how exactly the thing has to be done. But in a declarative system, as in a logic, we make some assertions. Okay, we make some assertions, we make some statements. Now, which statement has to be executed at which point of time is not the headache of these rules. That headache will be transferred to another thing, another system called the control mechanism or the inference mechanism. That's why often this sort of knowledge representation is also called declarative knowledge representation, whereas the type of knowledge that we are embedding in the case of a program is often called procedural knowledge representation. However, in this case we can see that rule based systems can be of this form. If this is the case, that means the condition, then do this. This is one way of stating that. It is also possible to state in this way, that do this, all right. But we can also make some assertions over here, and as I said just now, that these rules are just some declarations which do not say how the thing has to be done. We require a special interpreter which I just now said as a control mechanism, okay, controls There are different names for it: control mechanism, inference engine, inference machine, different names, but the purpose is the same. That's a procedural block of knowledge that interprets these rules, that applies these rules as the case may be. Now, we can have very simple rules which are very similar to the rules in logic, but we can think of, now what can a rule do? A particular rule has got, if you recall, a rule has got the left hand side part which we call the antecedent or the condition part, if this is the case. If this is the case, that is, if it is really true that this is the case, then on the other side of the implication, some actions may be stated: shut off the heater, open the window, close the tap, okay? Or we can infer, we can make some assertions: the boy is intelligent, the season is monsoon, okay? Consider a rule: if it is raining every day, then possibly the season is monsoon, all right? Or if it is monsoon, then there is high chance that there will be rain today. Now the condition is, if the season is monsoon, and suppose my fact is it is really the month of July, which is the season of monsoon, so the fact is true. So given this fact to be true, we can infer a new fact that possibly it will rain today. That's another fact, but that we are inferring, but we are not stating any action as we had done if the right hand side were shut off the heater, open the tap, etc. So a rule, a consequent of a rule can be either an action or can be a new fact. If it be an action, that action is taken by the interpreter, that action is executed by the interpreter, and if it is a fact, then that fact is added to the fact base of the rule based system. All right. Also, another important thing is that along with the facts, degrees of certainties can be associated. Just now in the course of discussion, I have stated a rule: if the season is monsoon, then it is possible that it will rain today. I can make a statement in different ways, the same statement. If the season is monsoon, then there is 60% chance of raining today. I can also say, if the season is monsoon, then it's highly probable that it will rain today. Now these are, you see that it will rain today is not coming as it is, but I am also adding some possibilities, some certainties with this statement. So when I infer a new fact, what is the new fact that I am inferring? Given that the season is monsoon, my fact that will be inferred will be possibly it will rain today. It's 60% probable that it will rain today, etc., etc., etc. So it's possible that I can associate some sort of uncertainties with these rules. Now let's again think back what happened to logic. In simple propositional logic or predicate logic, we had an assertion which could either be evaluated to be true or false. These were the two possibilities. There was nothing in between. But here, along with these facts, I can add on some certainties. In a separate lecture later on, we will see how we can, in an intelligent system, how we can handle such uncertainties. So we just, for the time being, we remember that in the case of rules or rule based system, when we infer a fact, this can be a hard fact which can be either true or false, or it can be a fact which is associated with some sort of certainty, some degree of belief or disbelief, whatever it is. Okay? So it's no longer black and white decision, there can be a gray region in between. Now, we can have also different control strategies which are often heuristic. We often need to take decisions in real world where we do not have all the possible information that we need. Often we have got very partial information about a scenario. Suppose you want to travel from a place A to place B. You know some facts that there is a bus route from A to B, and there is also a train, railways connecting A to B. You do not know exactly what the fares are, but if you really need to save money, then probably you will select bus travel, because your other domain knowledge in general tells you that bus travel is often cheaper than train travel. May not always be true, but let us assume that that is a scenario. So you have got some partial information, and based on this partial information and the other domain specific knowledge that you might have got through some other means or general knowledge that you have, there are some thumb rules of making decisions, and we often use those to take the decisions, and we can say, well, probably bus will be cheaper mode of travel, so going from A to B for low cost, bus would be a better way of going. Now, these sort of decisions that we often make may not always have a very strong logical basis, but these are often very much practical, and we often take such decisions. All right. So, these are we'll encounter this scenario time and again. This term for this is heuristic. All right, and such heuristics will be employing for rule based systems as well, for different control schemes we will see. Now, let us see, here is an example of a rule based system. If it rains today, the roads will be wet today. This is clearly understood when we write in English. We can write this in the form of logic as rains, which is a predicate. Rains today implies implication wet road today. Or in the form of a rule we can say if rains today, then wet road today. Now, you see the correspondence between this logic statement and this rule. All right. Again, this is one rule. There is another rule that I have added here. If rains today and not covered roads, that is, if the roads are not covered, then wet road today. Now, look at the difference between these two rules. This rule is obviously more specific, because it says that the road will be wet today if it rains today and the roads are not covered, whereas this is a statement which is much weaker. If rains today, then wet road today. Okay. Now, look at the antecedent part of this rule. Rains today is an antecedent and wet road today is a consequent. All right. In this case, we have got a number of antecedents, rains today and not covered roads. These are two antecedents, and these two together we call the antecedent field, or simply we call them antecedent. Now, what happens to this rule? If the fact is that rains today, that means if rains today evaluates to true, then we will conclude that the roads will be wet today, this part, okay, wet road today. On the other hand, here, when will we infer wet road today? We will infer wet road today if both these conjuncts of this antecedent evaluate to be true. In our discussion, I will often refer to this to be the antecedent part or the antecedent field, and each of them are individual antecedents. Now, when does this rule really work? This rule will be active when both these antecedents, since they are connected with an and, are both true. Suppose the fact is it rains today and the roads are covered today. In that case, according to this rule, this part will be true, but this part will not be true because the roads are covered. Then I cannot really infer that the road will be wet today. Okay. So, in a rule we have got two parts. One is the antecedent part and there is the consequent part. The antecedent part can consist of one fact or can be a conjunct of facts or anti-conditions. Okay. And look at this consequent. I was just now talking of two different types of consequence. Some things can be actions and something can be assertion. Wet road today is simply an assertion that is adding to my collection of facts. And so, since I know it rained today and not covered today, I know one more fact, that the road is wet today. Okay. Might be there is another rule, if it is wet road today, then wear good shoes or something of the sort. So that I can, so this fact can be used further to infer something more. Now, which are the facts here? I have already said that facts are which are already known a priori, but you can see that facts are also generated, just as in this case, in this example, wet road today is a new fact that has been generated. All right. So now, I hope all of you recall what is meant by modus ponens, which was a very common deduction mechanism that we talked about when we are talking about logical inferencing. Here we just revisit modus ponens for a second. Let's see. Here you see P implies Q and P. So P implies Q is an implication and P is a fact that is given. So given these two, using modus ponens, what can we infer? We infer Q. That means if P is true, then Q is true. And since P is true, we infer Q is true. Now suppose there is another rule, Q implies R. That means if Q is true, then R is true. Now here from these two, we have inferred Q, and again from these two, we can infer R. So you can see that if we consider this to be a rule and this to be a fact, then we can infer a new fact. And using this fact and another rule, which rule? The rule which has got this one, this fact Q as its antecedent, we can infer another fact R. So you can see, therefore, starting from this fact, given fact P, and these two rules, P implies Q and Q implies R, I can infer first Q and then R. So this sort of this rule is allowing me to infer Q, and inferring Q is allowing me to infer R. So this phenomenon is also known as rule chaining, where we are inferring a fact using a rule, new fact using a rule, and with the newly inferred rule, I am with a newly inferred fact, I am applying another rule and inferring a new fact, and the chain can go on. Okay. So let's now come to rule-based systems once again. Now, rule-based systems are also known as production systems. Those of you who have worked on compiler, you have seen that often grammars are specified in the form called Backus-Naur form, which is also a set of productions. I leave it to you to find the similarity between those statements which are given in Backus-Naur form and the type of rules that we will be discussing. Certainly there are quite a few similarities. Now you see, a rule-based system, which is also known as production system, is a system whose knowledge base is represented as a set of rules and facts. So we were talking about knowledge representation earlier. Logic was one form of knowledge representation. We will see different other types of knowledge representation as well. Now, rule-based system is therefore one type of knowledge representation where the knowledge is represented as a set of rules and a set of facts. Now, we have already seen this. A rule-based system consists of a collection of rules which are in if-then form and a collection of facts And now with these rules and facts, we would not be able to infer anything unless there is another interpreter or control engine, whatever name you give it, inference mechanism, which will look at these facts and see which rule is applicable now and apply that particular rule and generate a new fact. Because in my rule base, I'll have thousands of rules. Now, given a particular objective, a particular problem that I want to solve, all these rules may not be relevant. So it is essential that I have to find out only those rules which are relevant at this particular point of application. So that task is done by the interpreter. And in today's lecture, we'll see how the interpreter applies these rules, how the interpreter selects these rules, and what does this interpreter really do to infer new facts and thereby solve some problems. Okay. Now, as I said, the rules are represented in the following form: if antecedent, then consequent. And antecedent can be a conjunction of a number of antecedents. Okay. When the antecedent part is null, it's also possible that I'll just have then this, or I just have a consequent. If the antecedent part is null, then obviously it becomes a fact. That's a true fact. A fact in general will assume that a fact is true. Okay. Now, a rule says that if these conditions are true, then I can infer a new fact. But if no conditions are given, then that consequence stands on its own merit, on its own right. So it's true, it's fact. All right. Some of you might recall, if you have written, those of you have written C programs, while one, while true, those sort of structures, which is always true. So similarly, if there is no condition attached to a rule, then it becomes a mere fact. All right. Now, here is a statement that I am making. Rules are normally represented as horn clause. There is a reason for this. I'll introduce horn clause, but before that, I assume that you recall what a clause is, a clausal form. A clausal form consists of a disjunction of literals. A disjunction of literals, for example, P or not Q or R, that's a clause. All right, that's a particular form. And implications can also be converted to clausal form. Horn clause is a particular form of such clauses, and it's preferred that rule-based systems be based on horn clauses. Let's see what it means. Look at this implication: P implies Q. Now, the clausal form of this, you will recollect, is not P or Q, because this implication, just as for the sake of revision, it means that if P is true, then Q is true. All right. Now, if P is true, then Q is true. Otherwise, P is not true. So, not P or Q. That's a clausal form. Similarly, P and Q implies R. It's a rule form. I can convert it to the clausal form not P or not Q or R. This is a clausal form. Now, look at this. P and Q implies R or S. If I convert it to clausal form, it becomes not P or not Q or R or S. Now, this is not a horn clause. What is a horn clause? First, let's look at that. Horn clauses, first of all, they must be clauses. That's why I've underlined it. There must be clauses. Horn clauses can have at most one non-negative literal. At most one non-negative literal. Look over here. Here we have Q is a non-negative literal. Here R is a non-negative literal. there is only one non-negative literal. But in this case, we have got two non-negative literals. So this is not a horn clause. So these are acceptable rules, but this is not typically in a rule-based system. It's not the case that you cannot write rules like this, but usually it is not encouraged, and the reason is there are some severe consequences to this, but I am not going into that in this lecture. But simply let us try to see, if I use this particular form which is not a horn clause because it has got more than one non-negative literal, what is the problem? Suppose my fact base says that the person is rich, that is P, and the person is large-hearted. Okay? So P and Q. Then the person will make donation, or the person will build up a school or whatever. So there are two possible implications that we can take. Now in the case of an implementation or execution, the interpreter will really be in a problem to select which one of these consequences it should infer. Should it infer both? Because I do not know whether both of them are true. This part will be true if any one of them is true. Or should it infer any one? If it has to infer any one, then which one should it infer? All right. So those problems really crop up, but those problems are absent in this cases. P implies Q or P and Q implies R. So we usually stick to horn clauses. That means in the consequent part we would not keep a disjunction. Okay. Now there are two more terms which we should first understand. Try to imagine, I mean, the rule, for a rule based system we have got a rule base and we have got a set of facts which we keep in a fact base. All right. Now these rules are evaluated to be true. Now when is a rule applicable? A rule is applicable when all its conditions evaluate to true. If any of the conditions evaluate to false, then that rule is not applicable. Now it may be the situation that given a set of facts and the set of rules, more than one rules can have their conditions satisfied. So more than one rules are applicable. We call that these rules are triggered, and out of these triggered rules, that means those rules are all enabled to be fired. Now when we apply a particular rule, we say that that rule is fired. And what happens when a rule is fired? When a rule is fired, then the consequent part, whatever is specified in the consequent, is inferred or that action is taken. So if it is inferred, if that new fact is inferred, that then this fact is added to the fact base. If a new if the rule just specifies some action, and if that action is taken, that action creates some state change. For example, if I, as I was giving the example, put off the heater, then the heater is put off. So the state change is that earlier the heater was on, and I change that fact, I delete that fact, heater is on, and add a new fact, heater is off. So in either case, there is a change in the fact base when a rule is fired. But it is not the case that all the rules which are enabled are fired. I can either fire any one of them. If I have to fire any one of them, I have to make a decision as to which one I should fire. All these things are there. But first of all, let's make a distinction that a rule is triggered when all its antecedents evaluate to true, and the rule is fired when the action stated in the consequent part or the inference related to the consequent part is inferred or is taken. Okay. So we'll make a distinction between these two. Now look at this architecture. This is an overall architecture of a rule-based system. You can see, look at this big rectangle. This is known as, forget about the rules which are written over here, forget about this for the time being. These rules, all these rules that are here constitute the rule base, whereas we can have a number of facts stored, and that is known as a fact base, and here there is a procedural component which can, as I said, which can have different names: control scheme, interpreter, inference machine, control engine. There are different rules, different names which are given to this. Now you see, look at these arrows. What does this control scheme do, or the interpreter do? It is looking at the facts and looking at the rules, and is trying to see, given the particular set of facts, which are the rules which are applicable, which are triggered. Now, out of the rules which are triggered, it will fire one or more than one, and consequently when the rule is fired, a new fact will be generated, and that will update this fact base. So at the top level, we look at three components in a rule based system: the rule base, the fact base, and an inference machine. Okay, these are the three basic components of a rule based system. Next, let's look into these rules. Here the rule is, if hot and smoky, if hot and smoky, then add fire. Rule 2 says, if alarm beeps, then add smoky. Rule 3 says, if fire, then add switch on sprinkler. So here we are talking of a toy problem where we have got an intelligent system installed, rule-based intelligent system installed, which has got some sensors put on in the room, and is sensing temperature. It's trying to see whether the temperature has become very hot. It's also there are smoke detectors. So it is trying to see whether there is any fire, and if it infers that there is fire, it will automatically start on sprinkler, or it will set up an alarm which will make people run and start the sprinklers on. So that sort of scenario. So we have modeled that using a toy problem. We have modeled it with these three rules. And what is there in the fact base? Alarm, beeps, and hot. So there are two facts. One is alarm, beeps, and hot. Now let's see. If since the alarm beeps, what is this control scheme? What will this control scheme do? It will look at these rules. Now which rule is enabled? I can see also hot. All right. So this rule has got this antecedent satisfied. If hot, yes, true. So this is satisfied. And smoky, well, I do not know anything about smoky here in my database of facts. So I cannot say that it is smoky. So this part is true, hot is true, but the smoky is false. So this antecedent part of this rule is not completely satisfied, right? It's not completely satisfied. So this rule does not apply. Next, so it looks at, so it cannot, this rule is not triggered. It comes to the second rule. If alarm beeps, well, looks at the fact base, alarm beeps is there, so this part is true. So this rule is obviously enabled because it has got no other antecedents. This entire antecedent field, this antecedent part is satisfied. Well, let's look at the third rule. If fire, well, no, I do not know anything about fire here, nothing is here. So this antecedent is also not true. So this rule is also not triggered. In this case, we have got only one rule that is triggered, that's rule R2. So the control scheme then finds that only R2 is triggered, so it has got no choice, it fires that. And what does this, what is the consequent part of this rule R2? The consequent part says, if alarm beeps, then add Smoky. So it immediately adds, when it fires, it adds to the database a new fact, Smoky. And you can well guess what will happen next. The control scheme will next look at again which rules are being enabled afresh. Hot is true, so this part is true, and now Smoky is also true. Since Smoky is true, this entire antecedent part is true, it is then, it will, okay, this rule is R2 is also true, but R2 is already fired. So we are taking up the strategy that I will not fire the rule, one rule time and again. It tries for the third rule, fire. No, I cannot, I have got nothing in the database as yet which tells that there is a fire. So only this rule is enabled, this rule is fired. And what is the consequent of this rule? Add fire. So a new fact is added to the fact base which says fire. So what am I inferring? I am inferring that yes, there is a fire. Now I again go back to this cycle and look at this third rule. The third rule is now enabled. If fire, then add switch on sprinklers. So now this third rule will fire and sprinkler on will be put in the database. So essentially this is the way in which a rule-based system will work. Now if you have noted this example very clearly, then you will realize that this can be modeled in the form of an automata of inferencing. Okay, and what is that automata? There are three phases. In the first phase, so what are the components that I have? I have got a set of rules, I have got a set of facts. Now what are the other components? And the inference machine is also there. So what is happening? First, the inference machine is looking at the fact base and the rule base and trying to find a match which of the rules are triggered. If it finds that more than one rules are triggered, then it will have to select some of the rules, maybe one rule or maybe a subset of these rules. And after that, let's, for the sake of simplicity, for the time being, let's assume that they are selecting only one rule. And that rule is then fired, that's executed. And when that rule is executed, what is happening? A new fact is being generated in the fact base. So we can essentially carry it on in the form of a cycle. So here is what is depicted. The inference machine or the interpreter, okay, is a machine that implements the strategies to utilize the knowledge base and derive new conclusions from it. Now how it is being done? Here is the automata of an inference machine. There are three phases. First is the match phase, then there is a conflict resolution phase, and then there is an execute phase. Now in the match phase, the inference machine is comparing the fact base and the rule base, and it will find out some rules which are matching. If no rules are matching, then we can't proceed any further. But suppose there is a set of rules which are matching, then those set of rules are being passed on, I mean will be used by the next state, which is the conflict resolution state. Where is the conflict? The conflict is among the rules. There are 5 rules which are triggered in the match phase. Now which of these rules I shall be firing? For that I need to have some strategy which is often called the heuristic strategy. Okay? We often use heuristic, but using heuristic, what we do is a conflict resolution strategy. I will be selecting one rule or more than one rule. Okay? Which of this subset of matched rules, which further subset I will be executing? That is decided in the conflict resolution phase. So we come to the conflict resolution phase, and after the conflict resolution phase, we decide on which rules to fire. And then with that information, we go to the next state, which is known as the execute state. In the execute state, those rules are fired, and when the rule is fired, see here in the match phase, we passed on only the triggered rules to the conflict resolution stage. Now, in the conflict resolution stage, we have resolved the conflicts and we have selected some rules to be fired, and when the rules are fired, then the firing causes a change in the, again, the new fact, in the fact base, new facts are added. All right. After that, so after this execute, we will again come to the match phase. But how long will it continue? So we'll come to the match phase, and in the match phase, again the matching will be done, and we'll see which rule is enabled again. We'll do conflict resolution, we'll do execute, and this cycle will continue. Now, how long will this cycle continue? This cycle will continue until the goal or the objective with which we are trying to solve the problem, the the problem that we have, we are trying to solve that we call a goal. As long as the goal is not met, we should try to do this. But it may be that we have not been able to solve the goal and we do not have enough rules at our hand. See, rules are essentially representation of knowledge, and knowledge is always limited, and often there are situations when we, the human beings, fail to solve a problem because of lack of knowledge, maybe at times. Okay. So, in those cases, we try till we exhaust all the knowledge components that we have. So, we will carry it on, but if we can solve a particular problem, then we will stop. Otherwise, we will exhaust our knowledge source and then stop. So, this scenario will, this cycle will continue. After every execution phase, it will go to this rule base, and after every execute, it will check for the goal, whether the goal is met. If the goal is met, then we will stop, otherwise we will carry on with this cycle. So, this is a very fundamental cycle of rule based system. Okay. So, here is a summary. The execute state fires the rules once all its antecedents match. Okay. And essentially the function of the execute state can be thought of as searching through a path to the goal in a search space. Here I have added a new name, search space. Okay. So, what I am trying to say here is that through these rules, we are essentially trying to depict all the possible ways in which a problem can be solved. Our objective is to solve a particular problem, that is a goal. Okay? And in order to do that, there may be different alternative paths. All the paths may not lead me to the goal, but there are paths which may lead me to the goal. So, effectively, our task is to search through this entire space, which I am calling the search space. Now, here is a search space denoted. Typically, a search space that is denoted by these states, you can see. Now, this state that I am showing is the start state. Say that this start state, and I have got a goal state also here. This orange node is a goal state, and this root node of this is a goal state, is a start state. Now, the start state, what do I have at the start state? I have got my rules, and I know about the goal, and right now this goal is not solved. Okay. So, I start my rule based system from here, and with the facts that I have and the rules that I have, I try to see which are the rules which are applicable, which are triggered. Suppose at this point 3 rules are triggered. I have just named only 2 of them, one is R1 and is R5. So, but I am denoting using this tree structure, this set of rules. Okay. So, I can take now, so I can see what this one shows is that at this state, the result of my match, which I was showing here, this match has resulted into 3 rules which are being passed to this conflict resolution module. And in that, I have, suppose I have resolved in favor of R1. So I can come to R1, and when I fire R1, a particular rule R1, I will be adding new facts to the rule. So I will continuously refer to this diagram. So I have resolved in favor of R1, and that has been executed, and new facts have been added to this fact base, okay, and that might have enabled me with 2 other rules, and I can select any one of them. Suppose I have selected this one, that, and I fired this rule. So here there was again a conflict. At this state, again a match has been done, and 2 rules have succeeded. These are triggered given this new state, and I have fired this rule and have come to a new state. Okay, and as I come to this new state, and if I fire this rule, I will come to the goal node. I will come to the goal node. So this is now, but what are my possibilities? The possibilities are that I could have followed this path, I could have followed this path. Please follow the mouse pointer. This path, or might be at this conflict resolution strategy I could have followed another path. Suppose I, at this point, after firing R1, I come to a new state, and I fire a new rule, and I fire this rule and come to a state from where I do not find any other rule to fire. Then I cannot, what do? I cannot do anything. Let us say, but I think I can do some things. Suppose at this point R1, suppose this is R2 and R5, all these 3 were enabled, but I have selected in favor of R5, and I have come to this point. And when I come to this node, after match I do not find any rule that is enabled. So I cannot proceed any further. My goal, I cannot reach my goal. But what can I do? What can I do? What I can do is this. From here I can go back to the, since this is a dead end and I am not finding any other rule to fire, I can go back to the earlier node to see which are the other possibilities that have been left unexplored. For example, I came to this node, but I found I resolved the conflict in favor of R5 and have come to a dead end. So I go back to the starting node and see, well, what were the other choices that I could explore. If I really remember that yes, there were other alternative paths like R1, R2, etc., and explore these paths, then possibly I could find the path to the goal. Actually, this is what we do in our real life, and this phenomenon is known as backtracking. We often make wrong choices, but when we find that this wrong choice is leading me to a dead end, we revise our earlier decision, and this is known as backtracking. And what I have depicted over here is the search space and how the rules really traverse the possible search space, and my success will really lie on how fast I can arrive at the goal from the starting state. So what we have just now learned is that is the phenomenon of backtracking. If the inference machine reaches a dead end, that is, no new rule is enabled and the goal is not met. If the goal is met, then I am successful. If the goal is not met, then we will backtrack to the earlier node, as we have done here. We will backtrack to the earlier node and see whether there are some unexplored possibilities, and we will be exploring that. Okay? And so backtracking is a very important methodology of really exploring the search space, because it's often not possible to really make the correct choice all the time. It may not always be possible. So we will select the rules which are not proper given a particular context. And obviously, conflict resolution strategy plays a crucial role over here. If we have a good conflict resolution strategy, then obviously the backtracking will be reduced. If we have good conflict resolution strategy, then we'll be reducing the backtracking. Now, in this lecture, we conclude at this point where I have just tried to give you an overview of what rule-based systems are and how they work. In the next lecture, we'll look into other aspects. We'll look into more examples. We'll look into more details of inference mechanism. But I hope that you have understood how a set of rules really help us in solving the problem. You should remember a couple of things: the distinction between rules and facts, the distinction between match phase, conflict resolution strategy, and execution strategy. You must understand what is an inference mechanism. An inference mechanism actually selects the rules to be fired from given a set of facts. So, given all these, we'll move on to the next lecture where we'll be going into more details of rule-based systems.